As our next speaker, it's a pleasure to introduce Scott Sheffield from MIT. Scott has completed his PhD in Stanford under the direction of Amir Dembo, after which he had positions in various places, including the Institute for Advanced Studies and the Courant Institute, before moving to MIT in 2008. Scott's work has been recognized with a number of prestigious awards, including the Rollo Davidson Prize, the Sloan Research Fellowship, a Presidential Early Career Award, the Liouville Prize, a Slimon Fellowship, and a Clay Research Award. Scott has worked in many different areas of mathematics, but I think it's fair to say that the work that has become the most prominent is his research in conformal probability, where he made an extremely large number of contributions. And these include, for example, the development of imaginary geometry, the study of conformal loop ensembles, the definition of quantum Liouville evolutions, and the study of Liouville quantum gravity surfaces. And today, he's going to tell us what is a random surface.
Good morning, everyone. I know that you have been missing the talks already yesterday afternoon, but don't worry. This morning we have some very serious mathematical entertainment. So we start with the ICM plenary of Scott Sheffield. Please. Thank you.
Okay. Let's start. So today, I want to mention first, this talk is meant to be streamed as a plenary talk, so it's somewhat designed for an online audience. In fact, I'll even start with a bit of a clickbait flavor. Why is everyone talking about this 2014 comedy show clip? Some of you recognize this. This is when Stephen Colbert, as a comedian, told Edward Frankel, a mathematician, that he hated math. You won't believe what happened next. Frankel says, when people say, I hate math, what you're really saying is, I hate the way mathematics was taught to me. Imagine an art class in which they only teach you how to paint a wall or fence, but never show you the paintings of the great masters. Then, of course, years later, you're going to say, I hate art. Colbert says, but in math, don't I have to know a fair amount of high-end math to appreciate the work of the masters? It's almost as if you could show me a painting by a master, but I don't have eyeballs yet. Don't you need to grow the math eyeballs to see the equations as beautiful? Well, today, the idea is to grow the math eyeballs that we need to understand and appreciate random surfaces. This is a big subject, combinatorics, graph theory, geometry, all kinds of physics, and so on. And we'll often use our literal eyeballs and try to figure out what are the right pictures to draw, simulations to view. How do we see these things in a literal sense? And then the metaphorical eyeballs will see how different pictures of the same object often lead to very different mathematical formulations and how these things are all related. We'll discuss random paths, trees, non-self-crossing paths. Now, if you Google what is a random surface, you can find, let's see here, I think I've got it here. Right, let's just try this. What is a random surface? Oh, I've got no internet here. Okay, never mind. I have it pulled up, though. If you Google it, you'll come up with my talk notes. So what is a random surface here? And if you kind of scroll down here, you'll find I have about 20 different survey articles. So Legal, Miramont Bayes, Holdenstein, various senior luminary people in the field have written articles describing various aspects of random surfaces. And if you want to really grow your math eyeballs, you can go to these notes. I've tried to make them accessible as an introduction, and then try to really read some of these 20 survey articles. And that's a good way, I think, for a young person to get started in this subject. Okay, let's go back to the slides. All right, and I also want to mention, too, there are 261 references in that article, which sounds like a lot, but it only scratches the surface. really a very, very large field. There are many thousands of things they could include, and it's almost painful how many things I wasn't able to include. If you Google my name, also you'll find these slides plus code for the figures, so you can go through them more slowly. When a constructor asks you, what is the canonical random path? The dialogue might go like this. Instructor, consider the simple random walk on Z. At each time step, a coin toss decides whether a position goes up or down. If you shrink the graph horizontally by a factor of C, vertically by root C, then the C infinity limit is a random path called Brownian motion, random function from R plus to R. Student says, great, but can you define Brownian motion directly in the continuum? Instructor says, sure, fix a finite collection of points, specify the joint law at those points by making increments, independent normals with the right means invariance. You can extend to a countable dense set with the Kolmogorov extension, then for all t by Kolmogorov extension. This is sort of what you would do in a first-year graduate probability class when you're formally defining Brownian motion. The student asks, are there other natural ways to characterize Brownian motion? And the instructor said, sure, it's canonical in that it's the only random path with certain symmetries, like stationarity, independence of increments, and it's universal in that by the central limit theorem, it's a limit of many discrete walks. So it comes up everywhere, finance, physics, biology, etc. Student says, what if I want a random path embedded in RD? Instructor says, easy, just use a vector, B1 through BD, of independent Brownian motions. For example, here's a Brownian loop. That's a Brownian motion that returns to the origin in the case D equals 2. And this D equals 2 case is especially interesting. Lawler, Schramm, and Werner, this was part of the work for the ICM 2006 Fields Medal, proved Mandelbrot's conjecture, which states that the outer boundary of this loop is a random curve, which is a form of SLE and has a fractal dimension of 4/3. Now the student is happy. Imagine, however, a similar dialogue about random surfaces. The student asks, what's the canonical random surface? This constructor says, well, you take a uniformly random triangulation of the sphere with n triangles. So I look among all ways to glue n triangles together along boundaries to make a topological sphere, choose one of them at random. So here's a 30,000 triangle example by Budzinski, given a 3D spring embedding. So that means you view every vertex as an electron with unit charge, and the edges as springs following Hooke's law. And you so the charges push them apart, but the springs hold them together, and you let it find an equilibrium state. And then you get a visualization of what this surface looks like. So the n goes to infinity limit of this random fractal surface is called the Brownian sphere, also a peanosphere, and a pure Liouville quantum gravity sphere, and a conformal field theory. The student says, you just listed 4 things. Which one is the n goes to infinity limit of this picture? The instructor says, well, they all are. The difference comes down to the features of the limit we keep track of. You view them as different aspects of the same universal object. 4 blind mathematicians feel the surface of an elephant, and they describe 4 different things. The Brownian sphere is a kind of random metric space. The peanosphere is a kind of gluing together of 2 trees. The Liouville quantum gravity sphere is a random Riemannian manifold. And a conformal field theory is a way of making sense of certain multi-point functions. And I'll say more about all these things later, so you can skip the text here for now. Technical point, we'll often in this talk be talking about the unit area random sphere. So that's a sample from a probability measure on a space of unit area sphere-homeomorphic surfaces. But there's also an unrestricted area version. And sometimes you allow the area itself to be random. And when K is a marked surface with endpoints, the natural measure is on area is a to the minus 7/2 plus K dA. And the exponent is motivated by discrete models. If you look at the number of triangulations with endpoints, then that number is going to scale. Well, there will be an exponential factor. But if you take that exponential factor out, it scales like this polynomial, which is n to the minus 7/2 plus K, where K is the number of marked points. Often also there's an off-critical case where you also weight by e to the minus mu times a, where mu is some constant. This comes up in Poyakov's early works, where mu is called the cosmological constant in the physics formulations. Okay, but moving on from that. the student asks, do I really have to learn all 4 of these different viewpoints? And the answer is, well, honestly, a lot of great work has been done by people who are only fluent in one of the 4. But all 4 do have important applications. For example, metric properties. There's the Brownian sphere, statistical physics, conformal probability, and so forth. Are they all characterized by simple axioms like Brownian motion is? And a student says yes, but actually each viewpoint comes with its own axioms, its own history, its own survey articles, and the proofs that these things agree with each other are pretty long and involved. Student, can any of the viewpoints describe a random surface embedded in RD? The instructor says, sure. So you start by weighting the law of the surface by the number of ways to embed it, RD, which formally involves weighting by the dth power of a certain partition function. This turns out to make sense for all real numbers d. The surfaces become rougher when d is large, smoother when d is small, converging to the Euclidean sphere as d goes to minus infinity. They're defined as random metric spaces when d is equal to or less than 25, but only as finite diameter, finite volume surfaces if d is less than or equal to 1. Student says, I'm getting lost. Can you give me those 4 definitions that you promised? Okay, so everyone take a deep breath. We now start the 4 definitions, beginning with the Brownian sphere. So first, planar maps and Tutt's enumeration. So a planar map is a finite graph embedded in the plane, where 2 embeddings are equivalent if an orientation-preserving homeomorphism of C union infinity takes one to the other. The figures below are isomorphic as graphs, but they represent different planar maps. Planar map is determined by a graph plus a clockwise cyclic ordering of the edges surrounding each vertex. So the number of planar maps with n edges is finite. To eliminate the ambiguity from non-trivial automorphisms, we'll often specify a root by fixing one oriented edge and calling that the sort of root of the picture. Now, if I gave you a map of countries, like the map of South America, you could draw a vertex in the center of every country and an edge between countries that have a non-trivial border. And there's a famous 4-color conjecture that all planar maps are 4-colorable. This was formulated by Guthrie in 1852. Progress was made by Tutt, and the computer-assisted proof came by Appel and Haken in 1976. This is maybe the most famous planar map problem of all. And what's great about it is that you can present it to a 6-year-old and have them completely 100% understand the statement of the proof. But it took over a century for people to prove it. It drove the math world crazy for many decades. Now, Tutt in the 1960s was working on this, and for the first time said, why don't we just try to count all of the planar maps of a given size? And he found that the number of rooted planar maps with edges had this very nice formula, which is written on the screen here. Asymptotically, this formula grows like, well, there's an exponential factor, and this n to the minus 7/2 plus k, I mentioned before, with k equals 1. And that's basically because the root corresponds to a marked point. That's a special location on the surface. Now, vocabulary, a triangulation is a planar map where all the faces are triangles, and a quadrangulation is one where all the faces are quadrilaterals. The Brownian sphere is obtained as follows. So first, you take a uniformly random planar map. You choose uniformly from the set of all planar maps with a fixed number of edges, or you could do it similarly with triangulations, quadrangulations, etc. And you interpret this random quadrangulation as a metric measure space. So measure is counting measure on the vertices. The metric is just the graph distance metric, the shortest path between 2 points. And then a number of these co-authors here were able to make sense of a limit of this. So the Brownian sphere is what you get when you take the scaling limit with respect to this particular topology, Gromov, Hausdorff, Prokhorov. Don't worry if you don't know what that means, but just there's a particular way of taking a limit of these finite things to get a continuum random metric measure space. And so Benedict Stufler has made some particularly nice simulations of this that I can show you. So let me move over to here. I downloaded this to make it a little bit faster. Let's see, here's this one here, Brownian map. I click on this. If all goes well, it should open for us. Okay. And this here, I'll make it even bigger, is beauty that I hope you can appreciate with ordinary eyeballs. So this is embedded again with a sort of spring embedding, but it's colored according to this metric, meaning the distance from every point to the average of all the distance to all the other points. So the ones in the middle are orange, and that means they're close. The average distance to the other points is fairly small, where the ones on the periphery are blue, which means your average distance to all the other points is large. So you got to get a glimpse here of the metric space structure. I can't show you all pairs of distances, but this average thing, it really lets you get an idea of what this thing is as a metric space. Okay, let's go back to the slides here. Next topic, peanosphere. To warm up, mating of deterministic fractal trees. So both the Brownian sphere and peanosphere are defined in the continuum as matings of random fractal trees. But before we get into that, think about mating deterministic fractal trees. So Julia sets are defined as follows. You let K be the set of points that remain bounded under repeated application of phi z equals z squared plus z, where c is fixed. And you note that this phi fixes the set K, and it's also a 2-to-1 conformal map from the complement of K to itself. And the phi preimage of a small ball that intersects one of these K is going to be 2 small blobs intersecting K. And the preimage of that will be 4 blobs, etc. And that really explains this approximate self-similarity here. Different parts are the same up to a conformal map, which looks locally close to a multiple of the identity. Now, 2 Julia sets, it turns out, can be mated or glued together along their boundary to make a sphere, as these individuals showed. And Arnaud Cherita has made some very nice simulations of the gluing together of Julia sets, which I'd like to briefly show you. So let's pull up the pictures again. Here we're going to glue together these 2 fractal Julia sets. And let me make this full screen. Go back to the beginning here so you can see this. So these 2 Julia sets, they're going to come together. I gradually remove the space between them so that they sort of fill out. And the interface between them is going to be like a curve that sort of snakes between the 2. It hits itself. And you get this lovely sphere. Okay, but now what happens if we do the same thing for a pair of trees? So let's click on this. So these are tree-like Julia sets. And when they come together, you actually still get a topological sphere, surprisingly, but with a space-filling curve that snakes in between these 2 trees. It's a piano curve, which is why we call the gluing of them a peanosphere. Okay, let's go back to the slides here. Here's the Julia sets you see when you Google it. And here's a picture of a Julia set. And I want to point out quickly that you can just take a few lines of code. Like here, let me copy this code here. Control C. Copy that code, and then you can go over to Mathematica. Here I have it here. Do Control V. There we go. And hit Enter. And I hope this works. Actually, let me do it on a slightly smaller version so it goes faster. Let's say 500. And I hope this works. Yes, it worked. Okay, we have here a surface. And you could then think, well, okay, what happens if you change that constant? Maybe change it from I to 0.8 times I or something. Hopefully we should get a different kind of Julia set. Yeah, it has kind of a dragon flavor to it. What if I want to give it a real part? Maybe I subtract, say, 0.1 or something. What's going to happen here? And it comes up a completely different looking Julia set. And if you want to kind of show your high school students or how you actually explore mathematics with technology, this is kind of a great way to do it. For all we know, we're the first people ever to look at this particular value for C. And we're kind of seeing some very kind of interesting behavior. Okay, Now let's go back here to these slides. Now the student asked, what's the canonical random tree? So Aldous, in 1993, just constructed a continuum random tree this way. You take a Brownian excursion, and you start with the graph of this thing, and you identify points that are connected by a horizontal line segment that lies below the graph, except at its endpoints. And the result is a random metric space, and the distance measures sort of how far up and down one has to go to get from one point to the other. A student asks, is there a discrete analog of this? And the professor says, yes. Just consider a tree embedded in the plane with n edges and a root. And let me just go draw this for you up here on the board quickly. So here's an example of a tree with 1, 2, 3, 4 edges. And I can trace the outer boundary of this tree as I like. So I take a path that goes around the tree as follows. And as I do that, the distance from the root will be going sort of up, up, down, up, down, up, down, down. So this is a graph of how the distance from the root varies in time. And if I take this picture and now glue together edges underneath this thing, I glue these things together, I glue the bottom together, then I recover the initial tree. So this is a very simple bijection between these planar trees and these walks that start at 0 and return to 0 at the end. Okay, going back here to the slides. So the Brownian tree is really the limit of this uniformly random planar tree that I showed you on the board as n goes to infinity. Okay, now mating trees. So imagine I take two independent Brownian excursions. I'll draw one like this and one like this, glue them together and make these two trees. And now imagine I draw these vertical red lines connecting them. And so I'm going to basically glue the boundary of one tree to another, as we did in the deterministic picture. And I'll just kind of declare points along the same line segment to be equivalent. So if you think about it, the outer boundary is all equivalent to a single point because I've got these 4 lines that are all equivalent to each other. But then there are also other equivalents. If I take a horizontal line here and the vertical lines it's connected to, that will also be an equivalence class. And the resulting structure, when you take the quotient topology with respect to this equivalence class, turns out, perhaps surprisingly, to be a sphere with a space-filling path. So as you go through the points, these red lines from left to right, each one corresponds to a single point in the quotient, that gives you a space-filling curve on the topological sphere. Now there's we call that a peanosphere. There's a theorem due to Moore from 1925 that gives you a very general set of criteria for when you get a sphere when you take a topological quotient, when you put a bunch of equivalence classes, and it's kind of not too hard to check that this satisfies that. So it's kind of easy to see you get a topological sphere when you glue together this pair of trees. Now on a discrete level, there's another correspondence I want you to know. So if you take any planar map drawn like this here on the top left, you can put a red dot in the center of every face and then draw a green line segment from each red dot to all of the blue vertices along its boundary. Then, if you erase the black lines, you're left with this down here, which is a quadrangulation. And this is actually a one-to-one correspondence between quadrangulations and planar maps, where each edge up here corresponds to a quadrilateral down here. You can also take the dual map. So down here, this is bipartite. So the blue vertices are the original vertices. The red vertices are the original faces. And but if I connect all the red vertices along these diagonals, then what I get corresponds to the dual graph upstairs. Okay, so keep these pictures in mind, graph, dual graph, as I move to the next slide. So this is a discrete version of the mating of trees. So I take, let me go up to the board here again and tell you that I can imagine doing a random walk in Z2. So this is a picture, say, of Z2 plus, where I start at the origin and I kind of walk around a bunch of times until at some point at time n, I come back to the origin. Okay, so going back to the slides here, if I kind of draw the x-coordinate of that walk down here and a constant minus the y-coordinate upstairs, and I glue together these guys, I get a pair of trees. And the way the walk works, you always change either the x-coordinate or the y-coordinate, which means that each one of these bands here, either the top or bottom will stay fixed, and the other one will change by one. Which means when I do this gluing, this band here is going to become a triangle. These two things will get glued together, and I'll have two red lines and one black line. So this thing becomes a triangulation. And as kind of I walk through these red lines, I sort of go through all of the different triangles. It's bipartite, as before. And if I were to erase these trees, I'd be left with a quadrangulation. Okay, the blue tree is what I call the tree, and the green tree will be the dual spanning tree of the corresponding planar map that corresponds to that quadrangulation. So what I've just given you is actually a bijection between simple walks in Z2 plus that start and end at the origin, and pairs MT, where M is a rooted planar map and T is a spanning tree of M. And if I gave you a random X and Y n pair, that would give you a random pair M comma T. And the probability of the map M would be proportional to the number of spanning trees of M. Now, this turns out to be special, where I have a probability measure on n-edge maps, and the probability is proportional to the number of spanning trees of M. This is because of Kirchhoff's matrix tree theorem, which tells us that the number of spanning trees of M is a form of, or proportional to, what we call the Laplacian determinant so the determinant of the discrete Laplacian, which is defined as a matrix. And the classical result says the partition function of the Gaussian free field is this determinant Laplacian to the minus 1/2 power. So, and if we had d dimensions, it would be to the minus d half power. So that sort of means that the number of ways of embedding of this map in some sense, number in quotes, is given by this formula. Is Laplacian determinant to the minus d half over 2. So if the determinant Laplacian is large, that means you have a lot of spanning trees, which means you have relatively fewer ways to embed the surface. Okay. Now, the connected map with the smallest number of spanning trees is a tree. A tree only has one spanning tree. And so we think of maps with very few spanning trees as being somehow tree-like. And maps with a lot of spanning trees are somehow rougher, smoother and less tree-like. And so weirdly, if M tree is the tree-decorated map, weighting by the number of spanning trees is equivalent to weighting by this determinant to the minus d over 2 when d is equal to -2. So you could somehow say the tree-decorated surface is like the surface embedded in dimension -2. And then forget the bedding. Well, it doesn't make precise sense, but in terms of weighting this by a power, you can make sense of that for any power of any d you want. Okay, I want to mention too quickly, there's an unconstrained variance where you don't require, say, the xn stay strictly positive, and in that case, you just glue the edges together by kind of wrapping around. So you think of this thing as a cylinder, and again, you'll get a pair of trees glued together. Okay, well here I actually did that. I generated this kind of discrete approximation of a Brownian loop. I drew the trees, and up here is the mathematical code that makes these two pictures. And then if I do the identification, so I draw horizontal lines here, horizontal lines down here, I'll make a pair of trees, which another few lines of mathematical code lets you produce. So here are the pair of trees, one blue, one green. And then I can go further, and with a few more lines of code, draw some red edges that connect them, and use this spring embedding function and pop that up on the screen. Okay, and so here's what this looks like, and you can kind of see it have sort of a surface look to it. If I take away the red edges, I get just the quadrangulation. Here's an embedding of that. And I want to mention that for any of these pictures I get, if I type this little line below here, it makes a 3D animated GIF. And I will just for fun show you a couple of these pictures you get by doing that. Okay. So here is one of them with the colors. You see it spinning around here. And Here, let's do the other one without the colors, but with slightly more vertices. And it looks like this. And you can definitely see that it looks like a surface. But the interesting thing here is I didn't have to tell the computer it was going to be a surface. It just used the spring embedding, and that naturally kind of inflated the thing out into this sort of surface shape. And you can kind of see these lovely pictures. Again, if you want a project to show your students, this takes just a few lines of code, and it's all on the slides. You can generate these pictures and play around with them. And I use Mathematica, but there are many, many packages where you can do this sort of thing. Okay. All right, so let's exit that and go back here to the slides. Let's see, here we are. Oops, no. Which one is this slide? This one. Yes. Okay. Now, a nice thing I want to mention, if instead of taking xt and yt to be independent Brownian motions, you can also make them correlated Brownian motions. And as you vary the correlation coefficient, it gives you one parameter family of surfaces. And though it's not at all obvious, it turns out that changing this rho is equivalent to changing the d value. And as d goes from minus infinity up to 1, this rho value goes from minus 1 to 1. And so to explain why that is, I want you to look at me for a minute and look at my two hands and view them as functions. So that the contour of this hand is sort of like a function, like the contour of a tree. And my two hands are fairly correlated with each other. They're quite similar. And if I take one of these hands and turn it upside down like this, you have two trees. And if I take these trees and glue them together with the red edges, snap them to points, voila, I suddenly get basically just a tree, right? I get the original tree back when I glue the two trees, identical trees together. But suppose I take my hands and I shift one of the hands over ever so slightly. So now my hand and the shifted version of hands are negatively correlated. When one function goes up, the other goes down. And so now when I glue these two things together, I get something that looks much more like a sphere. Okay? And that's what's going on here. So as you vary the parameter, you go all the way from a Euclidean sphere on one end to kind of one of these very rougher random surfaces, tree-like surfaces on the other end. Okay, let's go back up here to the slides now. Okay, so in my intuition, highly correlated trees make rougher surfaces, anti-correlated trees make smoother surfaces. And sometimes decorated planar maps can be decorated by percolations, Ising model, and so forth, can be encoded by correlated pairs of trees. So I have for you here a bunch of interesting examples. You can click on some of these online. I'm just going to show you one of them. This corresponds to d equals minus 12 and a half. And I have another nice simulation. So because it's a smaller dimension, less than 1, we expect that it's going to look smoother, not quite as fractal, not quite as rough as the examples I showed you before. And here's what we get. This was done with 8 million vertices by master coder Stoufler. And again, things are colored according to this metric space for the average distance to all the other vertices. And you can see with 8 million vertices, you see a lot of very delicate, amazing fractal structure. But it's not quite as wild. You know, here the dimension, we expect the Hausdorff dimension to be less than 3 versus the other example where the Hausdorff dimension was 4. And so it's very hard to sort of embed it in 3 dimensions. Okay, let's go back here now to the slides. Okay, next, revisiting the Brownian map story. So there's this bijection that helps us enumerate rooted maps or quadrangulations instead of empty pairs. And it's similar to the Molen bijection, but with a few key caveats. So first, instead of letting xn and yn traverse lattice edges at each step, yn can change by plus minus 1, xn by 0 or plus minus 1. So technical point. Also, instead of drawing a horizontal green chords, I'm going to draw each chord from a point on the right to a point 1 height lower on the left. So from every vertex, I'll draw a green line, but it will start at a point and it'll go to the point 1 height below on the left. And this means that some of the bottom vertices, I have to draw a new vertex for them to connect to, which I draw down here. Okay? And the third, perhaps the most consequential constraint I put here, is that I'm going to insist that for every horizontal line here, blue line, if I look at the red lines that come downward from it, all of those lines connect to vertices of the same height. So this red line here, there are 3 red lines that go below it, and they all connect to lines of exactly the same height below. Okay. Now, if you think about it, that constraint means that if I glue together the blue thing to make a tree, then each vertex of the tree will have red edges that all connect to points of the same height below. And so I can just draw a number here, which is the height of the things below that it's connected to. And what I get here now is a tree with a bunch of labels on it. And now if I shrink the red edges to points, I get this picture here. And if I then erase the black edges, I'm left with a quadrangulation. Okay, and these paths up here in this kind of green tree all have their distance decreased by 1 at every step, which means this is a tree of geodesic paths from one to the other. So there's sort of a mating of trees where one of them is a geodesic tree, this green tree, and the other is the dual to that. Okay, and this is a bijection, and somehow since these decorated trees are easy to count, easy to simulate, then that makes it so that these Brownian maps, or these planar maps, are easy to count and simulate. Okay. Now, let me mention too, here quickly, that if I were to sort of walk around this tree, at every point, there's a path that goes back to the root. And that is a labeled path of some length. And one way to draw a labeled path is to draw a picture like this, where the height of this thing is the length of the path. And at each step, as I go up, the left-right position tells me the label. So here I start at a value, the label goes down, then up, 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 and then it stays the same, and then stays the same again. Okay, so here's a collection of labeled paths. And it turns out that you can define a random walk on this set of labeled paths, where half the time you go up, and then you choose it with a coin, decide which of the 3 directions to take, and then half the time you go down, and then you just delete the top edge. And you look at a walk like this. Okay, and it turns out that you can imagine doing a random walk on this where you condition to start and end at the empty snake. And the limit of that is going to be a picture called the Brownian snake. And the Brownian snake, if you look at the x and y coordinate of the head of this snake, those will be 2 functions. And if you can glue together the corresponding trees and take the metric quotient. So one of the trees is going to be the geodesic tree. View that as a metric space quotient with respect to the identities you get when you glue in the other tree. And that turns out to be what we call the Brownian sphere. Okay, so this is a very simple way of constructing this Brownian sphere from the Brownian snake, which is just the continual limit of this simple object up here. Okay, now a Liouville quantum gravity sphere as defined using the Gaussian free field. So first, these are some pictures drawn by David Gu, who was collaborating with S.T. Yao at Harvard at the time. And they took these classical works of sculpture and drew conformally maps from them to classical mathematical shapes like the sphere or the disk. And here you can see the head of Michelangelo's David conformally mapped onto the Euclidean sphere. Now, it turns out you can do this for any surface by the uniformization theorem. So I can take the surface, map it over to something like a disk if it has boundary. And what we call isothermal coordinates means I view the thing on the right as sort of my coordinate system. And any set on the left, the set A, gets mapped to a set down here. And I can write the metric down here, or the sort of the measure, as e to the rho z dz for some smooth function rho, where dz is the Euclidean, well, metric or measure, if you're thinking about measures. And so when I just integrate this function here, so this, rho z is sort of the log of the density function. So e to the rho z is the density function itself. It's a positive function. If I integrate this down here, I get the measure of the thing upstairs. And it turns out that if rho is 0, I just get the disk back. If rho is harmonic, then I get what we call a flat surface. And in general, the Laplacian of this surface, of this here, corresponds to the Gaussian curvature here in some way. Okay, and so if I want to choose a random surface, now I can just think of choosing a random function rho. And so if I want a surface to be a perturbation of a flat metric, I want to choose rho, which is somehow a perturbation of a harmonic function. And the natural way to do that turns out to be to take what we call the Gaussian free field. So this is a random surface, and the way you define it is you take a graph. Phi is a function from the graph to the real numbers. So maybe D is a subset of Z2 in this example. And you take so maybe if you have n vertices, then the set of these functions is like Rn, and you can put a density function on Rn, and the density function is just going to be proportional to e to the minus this minus a half times this Dirichlet energy, which is the sum over all edges of the height difference across that edge. So we call this, sometimes they call this the potential energy of a mesh of harmonic oscillators, if you know those terms. If you don't, it's okay. Just think of, you're just summing the square differences. And you take e to the minus that sum. And so when you choose a random thing from that thing, it turns out to be a Gaussian in high dimensions. And you get this kind of randomly fluctuating surface. And the limit, as the mesh size goes to 0, is this continuum thing, which is somehow standard Gauss with respect to this Dirichlet inner product. And that's called the Gaussian free field. It turns out it's very rough. It's not a function, but it's kind of a random generalized function. Now, Liouville quantum gravity is what you get when you take the measure defined by E to the some constant gamma times phi of Z. So where phi is some kind of Gaussian free field, and gamma is some constant between 0 and 2. And this was motivated by string theory. Polyakov introduced this in 1980. Although, of course, as is always the case, some things were clarified after Polyakov, some things were sort of predate Polyakov. So one of the things that predates Polyakov, for example, is this rigorous construction of this measure. So the e to gamma phi z dz as a field theory, or as a measure, goes back to at least 1971 by Herb Krohn, who constructed this rigorously for gamma between 0 and 2, and then Kahan later for 0 and 2. And there were various other people who used what we call quadratic actions, which give you something like a Gaussian free field for random surfaces. So Polyakov in particular gives credit to Douglas for some form of quadratic action. Now, but if you take this picture and you try to make a picture where every square here has about the same size with respect to the random measure. So I basically start with a square, I subdivide it into 4 squares, subdivide those into 4 squares, and continue until I get a square whose size is less than some constant, some fixed threshold. And what I end up getting is a whole bunch of squares that somehow all have roughly the same size with respect to this random measure. And so I color these things according to the number of divisions. And so here you look for different values of gamma. For large values, you see here, all of these big squares have about the same size as the tiny squares. So think this here is New York City or Tokyo, high density regions where you have lots of squares. And this here is Nebraska, Sahara Desert, low density regions where you have very few squares. So it doesn't make literal sense since phi it takes values in the space of distributions. But again, you make sense of this using a regularization procedure, and you get this very important random measure. And so formally, we're going to define a Liouville quantum gravity surface to be a pair, d comma phi, modulo a certain coordinate change rule. And in this random geometry defined this way, you can define areas, you can define lengths of curves, you can put metric structure. There are lots of things you can make sense of in this kind of random surface. Here, by the way, is the 6 lines of code that you need to construct this. All right, now here's the Mollem bijection. So remember, I did this before. You glue these things together on the top and bottom. You construct this pair of trees. And I want to stress here that as I go from left to right, I'm going through these edges one at a time. And so if I delete these 2 trees, I have a quadrangulation. And this is a way of going through the quadrilaterals one by one. And now I've actually done here, these are 6 more lines of code that produce for you this lovely, what we call the Smith embedding. Let me first tell you quickly what the Smith embedding here is. I have it up here on Wikipedia. Let's see. Here it is. Smith embedding. So this was also invented by Tutt along with some colleagues much earlier than the other work by Tutt I showed you. And what they showed is that if you take any graph like this, say a planar map with a top and a bottom, and you put a plus charge at the top and minus charge on the bottom, and so you have some current flowing through, think of these as unit resistors, you can put the voltage at every vertex, and you can define a square where the upper and lower heights are the voltages at the top and bottom, and the left and right locations are sort of how much flow there is to the left if you count the edge itself, and how much flow if you don't count the edge. And that gives you a bunch of squares that all fit together into a grid like this. So every square here corresponds to an edge here. And it turns out that this is somehow a discrete version of a conformal map. So it's one of the more natural discrete conformal maps that work for any kind of planar map here. All right. So let's go back to the slides here. So here, I've just done that for these tree pictures I do. I picked these two vertices, the root and the dual root, and one of them is going to be the top and one of them is the bottom. This will be sort of on a cylinder. And I make these lovely pictures. You see all these squares. And if I were to kind of click on this, here they're colored according to the order in which they're traversed by the space-filling curve. Here they're colored according to size. But if I click on this, or sorry, here let me just escape here and zoom in. You can kind of see there's this lovely fractal self-similarity structure. You know, as I zoom in further, it kind of looks similar to what it did on the large scale. Okay. Now here's the cylinder version, where I kind of wrap around the two sides. You see the thing is a cylinder. And with a few more lines of code, you get the Mercator projection of that cylinder. So this is a conformal map of the thing onto a sphere. And this is another way of visualizing a random surface. So again, using our physical eyeballs, if you look at this sort of thing, you think, oh, that you have some density of squares. Maybe this is sort of a measure on a sphere. Maybe I should think of a continuum surface as being a random measure on a sphere, or some sort of geometry parametrized by a sphere. So it has a conformal structure with lengths and areas. It's very different from what you see when you look at the metric space world and you're thinking just about distances. So again, different physical pictures give you different ways of thinking about these mathematically. When you try to combine the two, here's a picture by Jason Miller where he actually colored points. So he used one of these square tilings, but then he colors points according to their distance from the origin. And you kind of can see here, this is the metric structure together with the embedding. So the red points are far, green points are close, and so on. Okay, now it turns out that if you take this SLE decorated sphere is equivalent to the peanosphere. So SLE is a random curve defined as follows. If I give you a planar domain D, there's a path from A to B, which is a random path. We call it an SLE curve. And there's a parameter gamma that tells you roughly how windy the path is. And it's defined in the following way. So first we insist that this definition be invariant under conformal maps. If I map from a domain D to another one, I want the image of an SLE in this domain to be an SLE in the other domain. And then it's supposed to have this property that if I condition on the path up to a time, the conditional law of the rest of the path is an SLE in the domain left over. And what Oded Schramm proved is that there's a unique family of paths that satisfy these properties. There's an explicit construction that I won't get into here. You can look at the slides more slowly later. But I will tell you that they did manage to prove that when kappa is less than or equal to 4, you get a simple curve between 4 and 8, a curve that hits itself. And when it's bigger than or equal to 8, you get a nice space-filling curve. Okay. Now, let me mention too, if you use these two lines of code, you get a bond percolation, where basically you take a grid in ZD, and for every edge, you toss a coin to decide whether to include that edge or not. And you can also do the same thing with hexagons. So for every hexagon, you toss a coin to decide whether to color it, say, yellow or blue. And in this case, I've colored the left boundary all blue and the right boundary all yellow, and everything in between is now done with a coin toss. And so this path, this interface between these if you start at the bottom here, there's a path that is the interface between red and blue. And this path converges to SLE6. in the limit. So this is the work of Stas Smirnov. This is part of the work for the 2010 ICM Fields Medal. And kind of Kami and Newman finished the argument for the SLE6 part of it. And there's also something, the Ising model, which would, you can do the same sort of thing it's kind of a different way of coloring vertices or faces randomly, one of two colors. And then you get different kinds of interfaces. And these converge to forms of SLE3. There's a dual version that converges to SLE16/3. This is also work by Smirnov with many co-authors, including Chelkok, Duminil, Kopan, Hongler, Izyurov, Kempinen. Okay. And a lot of great work has been done, obviously, on this Ising model, a very important topic. Okay, here's a picture, by the way, of that percolation interface where I have colored the same way, but now this is done in the whole plane, and this path here is colored in red. Okay, now there's a different way of making a spanning tree, which is a space-filling tree, which is I take a uniform spanning tree and it's dual, and the tree is white, the dual is red, and there's actually a black curve that snakes in between the two, and that's a space-filling curve that traces out a continuous version of SLE. And here, Jason Miller drew one of these things with colors. All right, and here is this same sort of picture with instead of a square tiling, he did a circular embedding, and he got this picture here. All right. And again, you kind of see the space-filling curve, and a kind of important work by me and Jason and Bertrand Duplantier, or at least we thought was important, was we finally managed to show in a long paper that if you glue together two of these continuum random trees, you actually get a Liouville quantum gravity surface decorated by an independent space-filling SLE curve. Okay, so you actually do get this SLE and Liouville quantum gravity as a mating of these two trees. So it's a very, very long paper, but we managed to make that work. Now, let's get to the Polyakov measure. A student asks, how many ways to conformally embed a surface into the sphere? The instructor says, well, if A, B, C are 3 points on the sphere, E, F, G are 3 others, there's a unique way to take A, B, and C to E, F, G with a conformal map. And there's a Mobius group of all conformal automorphisms that has 6 real dimensions, infinite volume measure. The student says, well, can you somehow average over all possible embeddings? And the instructor says, yes. If F is any function of the embedded surface, you can write bracket F for the expectation with respect to the Haar measure embedded Liouville quantum gravity surface. So F is a function of phi, where phi is a zero mean Gaussian free field on this sphere. And it turns out that the phi for this has a very simple law. It's related to the Gaussian field. Don't worry about this too much for now. Now, the student says, how do you define the expectation with respect to an infinite measure? Well, you just integrate F with respect to this infinite measure. Okay, now show me these embeddings. And I want to show you now, here's some more pictures. So this here is a simulation where I take one of the marked points and move it back and forth. So one of them is fixed. I fix the top point and the derivative at the top and move the second. And you can kind of see here that if you had a sphere and you had 2 points, you could rotate one of them to the North Pole and use this kind of map to move the other one down to the South Pole. Okay, let's go back here and look at another picture. This is the same thing, but now I fix the North and the South Pole, and I make these things move up and down. Okay? And again, physical eyeballs, you kind of see what these different embeddings of this thing look like. And using this, by the way, you could take your third point and map it down to the equator. And then, unsurprisingly, if I go here, I can then rotate the third point on the equator to get to where I want to be. Okay, now let's go back to the slides here. Now, student says, suppose we fix the amount of area in a region. What's the expectation of that? Well, it turns out to be infinite. But the student says, what if you take a product? Say, what's the area parametrized by Finland times the area parametrized by Bolivia times the area parametrized by Mongolia? A student says, yes, now they're talking. So there are relatively many embeddings that assign a lot of mass to Finland, but relatively few embeddings that assign a lot of mass to all three of these countries at the same time. And because of that, the expected product here turns out to be infinite. And you can pull the integral outside of the expectation, and it's the integral over these certain multi-point functions, which is somehow the expected density at like 3 different points. And if you wanted to replace areas with balls, lengths of curves, then you would just use the same thing with different exponents, alpha I here. And the student asks, well, are all these kind of multi-functions easy to compute? And the instructor says, well, if I were just a Gaussian free field, then making sense of these multi-point functions would be easy. But once you fix the surface area and weight by the exponential, you get a very difficult non-Gaussian integral. And it's so difficult that it inspired a whole function called conformal field theory. Lots of amazing work on this. It's a huge subject with many ties to physics. A lot of people named here who've done a lot of amazing work recently. And I don't have time to really discuss it for you here, but I'll notice that if you click on this thing, there's a nice video by Vargas that really explains some of these remarkable new developments. Now, if you want to know very, very quickly what my own work in this subject has been, I've worked a lot on, for example, showing that these different objects are connected. So proving in joint work with Jason Miller and others that these different ways of defining surfaces are exactly the same. So it took us thousands of pages to prove all these things, but we now know that these different things are all equivalent. And there's been a lot of really spectacular work in recent decades, which again, I don't have time to explain for you, that really shows that these discrete models converge to these things in different ways. So I thank my co-authors and students who've done a lot of work here. I also want to maybe quickly thank here all the people who helped me improve the ICM notes, and the organizers, and the anonymous referees. And thanks to all of you for listening. That's the end.
Thanks, Scott, for this very beautiful talk. Are there questions? Yes.
Has it been looked into that if you in this mating tree picture, instead of taking Brownian excursion or Brownian like this path, you take some other like stochastic process and then try to do this mating construction and what comes out of them?
Yes, that's a very good question. So the question is, what if instead of using a pair of trees like this, you use a pair of Brownian trees, you use a different pair of random trees to glue together to make a surface. So I can tell you that if you use Levy processes, trees that have jumps, then it turns out that there's a way to do the gluing that gives you kind of a gluing of a tree of Liouville quantum gravity surfaces. And it looks kind of like the mating of those 2 Julia sets I showed you at the beginning, where you have kind of a tree of bubbles and the 2 trees of bubbles glued together. So that's something we have worked out carefully. There are other natural things you could do. You could try using fractional Brownian motion or other kinds of things, and we haven't looked into that. So there are plenty of natural questions you could ask that we really haven't done.
Any other questions? I come slowly.
So all of these discrete models you're talking about with these planar maps, you're starting on a sphere. If you were to start on a different genus surface, how much of this carries through to give you some other random
yes,
surface?
That's right. So everything I did here was in the genus 0 case, but these all have analogs for a higher genus. And if you look at the, if you Google what is a random surface and you find my slides or my lecture notes, you can see some references, kind of a partial list of references to this subject. So you can define a Brownian torus and or Liouville quantum gravity torus or 3-hole torus, 5-hole torus. These all extend. Sometimes computing these multi-point functions explicitly, or computing the law of the genus. These are kind of things that are very, or the law of the conformal class that you live in. These things are difficult. There's a lot of work that remains to be done. But I think a lot of the really amazing work that's been done recently in this subject involves precisely what you say, understanding these things. And that's true for all the different points of view, the conformal field theory, the Brownian side. These things are interesting in all those sides. And one thing I always regret about talks like this is I don't really have time to give credit to all of the young people doing exciting new work in this area. But there's been, just in the last few years, a lot of problems that were hopeless 10 years ago are now just being solved one after the other. And these connections from the physics side, the conformal field theory side is now being much more well understood than it was 10 years ago. And the combination with these points of view I discussed today is really, really helping us, I think, make progress on the problem you mentioned.
Any other questions? If not, let's thank Scott again.